let's discuss this previous example a little bit further. We have this function f of z, which is a Mobius transform mapping the unit disk onto itself, where z0 is equal to 1/2. And in this case, if we take f of z conjugate, then we of course obtain this expression, and by using standard rules for conjugation we obtain eventually that this is equal to the conjugate of f of z. So what does this mean geometrically? It means that if we have some point z in the z-plane which is mapped to some point w, then the conjugate of z is mapped onto the conjugate of w. Let me show you this in an illustration. We have this point z here, it's mapped onto w, then the symmetric point here, which is z conjugate, it's mapped onto w conjugate here. So we have the function f of z is symmetric. Is a symmetric mapping with respect to the real axis. Let me go into this unit circle once again. This unit circle is mapped onto the unit circle here. And let's now focus on one particular property of the function f of z. If we divide the top and bottom of this fraction by z and let z go to infinity, we easily see that this is going to 2. This means that if we are on some line, for example here, going through the point 1/2, 1/2 is the point where f of z is equal to 0 here, so 1/2 maps the point 0 here. If we now move along this vertical line going through this point and move to infinity, then we know that the function f of z will move to the point 2, which is placed here. So we have one point here at 0 and another point at 2. And we know that a straight line in a Mobius transform is transferred to either a straight line or a circle. So we know that this must be a circle in the UV plane. Moreover, due to the fact that this transformation is symmetric with respect to the real axis, we know that we must have this symmetry. The center of the circle must be on the real line. So then we know how we can illustrate the circle, the mapped circle in the UV plane for this straight line going through 1/2. Let's consider the red vertical line here going through the point 0. In this case we have we can find the mapped point at the pop point, which is mapped by 0, 2 times 0 minus 1 over 0 minus 2, that's just 1/2. So we know that the point 0 is mapped to this point 1/2. So then we have one point of it, of this circle, which this straight line is mapped onto, and we know the other point at infinity is, or corresponding to infinity, is this point here at 2, and we know the symmetry of the circle because this mapping is symmetric with respect to the real axis. So then we can sketch this curve, this circle. now it's very easy for us to do the same for this this straight line. It's going to be a circle like this. So in this way we can describe many curves. We can also describe horizontal curves in a similar fashion.